Go on, Amit.
So, good afternoon, everyone. Hope all of you are doing well. Thank you for joining with us in the penultimate talk of Final Camp of STEMS 2021. Today, we have Professor Shankar Bhamidi with us. Before we start the talk, let me give you a brief introduction about him. Professor Bhamidi is a professor in the Department of Statistics and Operations Research at the University of North Carolina, Chapel Hill. He obtained his PhD from the prestigious University of California, Berkeley, under the guidance of Professor David Eldos. His research interests are mainly in probability and statistics, specifically in stochastic process and random networks. Today, he will be giving a beautiful talk on the very crucial topic of networks, which have influenced our lives in the very recent years and in many ways. Hope all of you enjoyed the talk. And a small request: can you please turn on your video camera so that we can reach closer to a live interaction? And feel free to ask questions during the talk and put it in the chat also. We can take up with the professor. So over to you, professor.
Okay, yeah, thank you again for allowing me to speak. And so my screen is on this side. So if I don't seem to be facing the camera, it's just because I have another screen here. And yeah, please feel free to stop me at any point. I don't have, as I was telling Amik and Anuruddhan, I don't have an agenda that I have to finish all the slides or anything. So yeah, as Amik just now said, yeah, I work at this University of North Carolina at Chapel Hill. So maybe for people who are not familiar, North Carolina is a state on the east coast of the US. So if you have seen, say, movies like Hunger Games and stuff, these were filmed in North Carolina. So it's a very green, like full of forests, so to speak. And so on one side there's the Atlantic Ocean, on the other side there are the mountains. So it's a beautiful state on the east coast. And there are three big universities. So there is UNC Chapel Hill, where I am at, and then there's Duke University, and then there's North Carolina State University. So this is called the Research Triangle Park because there are these three big universities, and right in the middle are a ton of companies like IBM, GSK, and so on. So this is where I'm at, and as Amik said, so I did my PhD at Berkeley. We are probably familiar with this Golden Gate Bridge, which in any like Hollywood movie, in Planet of the Apes or Transformers, is one of the first things that's destroyed. So that's where I did my PhD. So this is on the left is my picture when I started my PhD, and then by the time I finished my PhD, I lost 5 pounds by just shaving my mustache, 5 kilograms by just shaving my mustache. And Professor Aldous is my advisor. He's on the right, in the right picture. And as I was talking to Amik, sort of, I would say my only claim to fame is, I'm so Professor B.V. Rao, who's a professor at CMI. I'm his son, and I would say he's been extremely influential in terms of the probability community in India. So that's my only claim to fame. Other than okay, so
I would like to interrupt here, and we have also Professor B.V. Rao with us today in the audience. So welcome, Professor B.V. Rao.
Yeah, I called him 20 minutes ago just to confirm that I'm speaking at 5 in the morning for me and not 7 in the morning. But yeah, thanks.
Sir, I think you're unmuted. You're muted. So could you unmute?
Yeah.
Okay, can you hear me?
Yeah, now it's perfect.
Okay, yeah. Not sure why it muted. Okay. So, so the plan for today is I'm going to tell you, why people care about networks. There's not going to be much like actual math here. I'm not going to define precisely concepts, but why people care about networks. And then maybe like my sided view in the sense, so I'm a probabilist in a statistics and operations research department. So what are the kinds of things that I work on? So I'll try to tell you a little bit of this. And then finally, towards the end, maybe I'll conclude the talk by giving some general advice about research, mainly through illustrating mistakes I made so that people don't make the same mistakes. So yeah, as I mentioned, anytime you have questions, stop me, or at the end of the talk, anything is fine. Okay, so the talk was titled Networks Everywhere. And so this networks, I would argue that networks have had a major impact on our lives. So for example, so air transportation networks. So this is sort of a GIF of air transportation networks at the start of the COVID era, so to speak, in February, where in March and April there was a huge drop in the transportation, like airlines, um, air transportation through the world, and then it again sort of picked up as time progressed. So here the networks are potentially locations like airports, and from these networks you have flows like airplanes or air traffic going from one part of the network to another. And of course these influence lots of things, for example, spread of epidemics through air transport networks, etc. um, Another example are brain networks, where um, you have locations in the brain. So, for example, neurons, which are connected to each other. And these neurons interact with each other. They send signals from one neuron to another. There are many, many different sorts of neurons. And each neuron itself might be very simple, but through the concerted activity of these neurons, you get emergent behavior. So if you think, you have each of these individual neurons interacting somehow, but through their collective interaction, now you get things like consciousness, you get memory, and so on. And so this is another example of networks. And I should mention, none of these pictures are mine. I've taken these from places like the link at the bottom. This is from Purdue University. So another place, another thing where networks have played a major role are things like social networks. So I've heard that there's again, yesterday there was a big earthquake in Japan, but a few years ago there was a Fukushima earthquake, which caused this big issue with the nuclear reactor there. But what this is sort of visualizing is like the flow of information on Twitter, from Fukushima, so or from Japan, I should say. That's the purple picture, and let me do this again. And flow of information from other places like the US or India and so on. Those are the green bits of information. So once again, the flow of information about any news activity, quite often now we see this through streaming on things like social networks like Twitter or Facebook, or even things like WhatsApp. So a few years ago, there was the whole the Arab Spring. Let's see if this actually plays. Oops. So this one, okay. So once again over here, the information about the Arab Spring, like how people were retweeting about various things that happened, Mubarak's resignation, etc. So slowly, this information also spread through Twitter. So slowly people started getting more and more information about what was happening in Egypt, and things sort of grew like this. So this is sort of maybe the field in which I work in. So generally trying to understand networks. So as I said, so as a probabilist in a statistics and operations research, what are my general goals and why do I wake up in the morning? So broadly speaking, these are four of my goals. So first is understanding models proposed by domain scientists. So I work with people in sociology, in political science, in neuroscience, in like business, in the business school, and so on, to sort of understand. So they're interested in models related to whatever they're working on. So let's say neuroscientist comes to me and says, this is what we're thinking about how the brain, or the data that we have, this is how we think we can model this data. Do you think it makes sense? So then I try to help them understand whether the model that they have thought of actually fits their motivations. The second sort of thing that I think about is understanding and developing algorithms to reconstruct network in the light of partial information. So by this I mean, and you'll see examples, in many cases you don't actually observe a network. You can only get indirect measurements of the network. And so from these indirect measurements, can you get a better picture of the network itself? The third thing that I do is think about algorithms to simulate models of networks. So quite often there is some data that people have. They think that they're going to try a particular model on that network data to see if their model fits well and gives them insight. So for this model, they have to run computer simulations to actually fit the model. And if this computer simulation takes more than 5 years, then, of course, the graduate student involved in this project would not graduate. So obviously trying to understand if the algorithms they're proposing make sense, that is another thing that I think about. And then finally, I hope that the kinds of mathematical techniques I develop could be used in other areas, not just restricted to the kinds of problems that I care about. So these are generally my goals. And the main message in the discipline that I work in, namely networks, is so much of the phenomenon is, so there is this word here called nonlinear, which doesn't really mean anything. I mean, nonlinear means not a straight line, but broadly speaking, so much of the evolution, much of the phenomenon on networks, these are very complex in the sense that one can think of very simple microscopic rules. You can say, okay, some people interact this way. But once you put it into a system, what happens after this cannot be predicted until you do the math. So very simple rules give rise to extremely complex phenomenon, similar to you have a bunch of neurons interacting to each other, and suddenly now you have memory or consciousness. And so in most cases, you actually have to do the math. So in the sense, you have to carefully think about what the model is, and you have to carefully think about trying to understand the phenomenon mathematically. Things like simulations, etc., can only give you some insight, and in many cases, they don't give you full insight. You actually have to sit down and sort of prove theorems or prove results to understand the phenomenon. Okay, so let me now start by giving you a few examples of areas that I work in. So the simplest example of a network is something called the Erdős-Rényi random graph. So what does this mean? So let me tell you a story. So suppose this is pre-COVID times. You have, let's say, 100 students in this program, in the STEM program. All of you come from different parts of India, so you don't know each other. You show up at CMI on day one, and if you're like me, with 99 other people, my main mode of operation would be to try to hide somewhere so that nobody sees me. But let's say you have these 100 people, each of whom are trying to interact with each other, form friendships as the program continues. So the way that these 100 people form connections is each person goes. So if it's Shankar, he looks at the other 99 people in the group, and with the same probability, he tries to talk with them. So talks to one person with some probability, then talks to another person with the same probability, and so on. And so with some people, Shankar does not talk. With other people, Shankar talks. So since there are 100 people, and the chance that Shankar talks with each one of them is some number p, on the average, Shankar at the end would have made 100 times p, or in general, m times p number of friends. So if m times p is less than 1, then typically what this means is, for a typical person, they don't have any friends, so they're not talking. So of course, there will be some people. So this is the average number of friends people have. So if the average number is less than 1, doesn't mean everyone is isolated from everyone else, but typically people are isolated. But you could say, okay, so what if we change from, let's say, the average number of friends is 0.999, then we expect that people in this network that is formed of friendships, typically people are isolated. But what if we change from 0.99999 to 1.00001? So on the average, people have just a little bit more than one friend. So if you do this simulation in the graph, so this is a simulation with 3,000 people instead of 100 people. So on the left is a situation where on the average people have 0.8 friends. So most people don't have many friends, but of course there will be some people who have some friends. And on the right, I've changed it to, on the average, people have 1.2 friends. So just moved it a little bit above 1. So just this little change from 0.8 to 1.2, suddenly you have this huge change in the structural properties of the social network. Okay, so this is an extremely simple model, and which has one parameter, which is on the average, how many friends do you have? I'm not no one was proposing that this is a great example of how a social network should look like, but this is maybe one of the simplest things you could think of. And even in this super simple setting, you see like completely unexpected behavior showing up. So in the 1960s, these two very famous mathematicians, Erdős and Renyi, who came up with this model, so they mathematically showed that amazing things happen when you transition from average number of friends being less than one to average number of friends being greater than one. And in particular, they showed, like mathematically proved, that there is an emergence of a big component, a big connected component of friends that happens when you go from below one to above one. So it's almost like, so if you took a physics course, then you know things like phase transitions. So if you have, say, water, and if you cool it to, let's say, minus 0.00001 degrees Celsius, then you get ice. If you heat it to 0.00001 degrees Celsius, suddenly it becomes liquid. So this is an example of a phase transition, and they show that the same sort of things also show up for things like networks. You have this phase transition phenomenon showing up. And
Sir,
okay, yep.
so there is a question in the chat that
Okay.
is the density of the chains in the in the previous slide, density of chains being higher towards the middle, a randomly generated fact?
No, good question. So the visualizations themselves. So one natural question is, these are 3,000 points. So how do you with some connections, or how do you visualize these 3,000 points? So there are very sophisticated computer algorithms. So I use something called graph tools from Python, which is extremely sophisticated, and it figures out how to put these 3,000 points to the corresponding edges. So how does it put it in on a picture? And so here, the points that are more central in the network, in some sense, those are put in the center of the picture, and the edges themselves. So things which are how to best explain this. So there's something called betweenness centrality of an edge, which means it measures how central that is for, if you think about this as a road network, how important is a particular edge in transmitting flow from one place in the network to another. So the size of the edge is corresponds to this measure, like how central it is. But yeah, this is just a design choice that I made when I was trying to visualize this. I don't know if that answers the question. Yeah.
I think that answers the question. Thank you.
Okay. Yeah. Thanks. Okay. So you could. So this is. So I told you a simple model of a network. You could think of a dynamic version. So what you're doing is, again, you have the story of 100 people coming to CMI. Initially, none of them know anyone else, and then slowly, as time progresses, they start forming connections. So initially, these two people start talking to each other. Then these two people start talking to each other, and they form friendship. And then you have this next friendship forming. And so when you have this next friendship forming, so now you have a group of three people who all know each other in some sense. And then one more person joins this group. So now you have one group consisting of 2 people and another group consisting of 4 people. And then one person in the first group talks to another person in the next group. And now suddenly you have, so these 2 groups combine into one group. Okay, and in the world of mathematics, what we're saying is you have these components. So you have these groups of people who are slowly forming, and at some point you could have groups merge into each other to form a big group of people. So this is a dynamic version of how groups form in social networks, for example. Now, it turns out, so you could ask, like, can we understand these sorts of these sorts of dynamic processes? So this is now a dynamic process. Can we understand these processes mathematically? So it turns out, yes, you can. It leads to beautiful mathematics. And the really interesting thing about trying to understand these simple phenomena mathematically is it turns out maybe 10 or 20 years before people were thinking about these social network questions, the same sort of question showed up in the world of colloidal chemistry. So in chemistry, people were interested in, suppose you have a bunch of oil droplets, which are suspended in some water, for example, some solution. Then these oil droplets slowly merge together to form bigger and bigger droplets, eventually leading to something called a gelation phenomenon, where you have a big gel forming. So in the world of colloidal chemistry, people were interested in such phenomenon. When does a gel form? What properties about the system predicts when these gels form? What are the properties of these gels, and so on? And these sort of questions, it turns out, are very intricately connected to the social network sort of connections. So 2 completely different fields, social networks or how people form friendships, and colloidal chemistry or gelation, these are connected because if you abstract away the underlying application, they have the same sort of behavior showing up in both of these. And if you can provide insight into one area, then you can provide insight into the other area as well. So this is so on this slide it says Aldous in 1996. So Aldous is my advisor. So he thought about the dynamic version of these networks, and he saw the connections between these things and what happens in areas like chemistry and so on. And in fact, he so for example, after realizing this mathematically, he spent, I think, about 2 months every day just sitting in the physics library at Berkeley, reading papers and papers on like chemistry and physics to try to connect these 2 areas. So it's a survey paper trying to connect the world of probability to the world of physics, chemistry, and so on with regards to these sorts of models. Okay, and I should mention, so I said I work on things like this. I won't tell you exactly what kinds of things we do, but one of the world's leading experts in these sorts of phenomenon, these sorts of models, is quite close or much closer to you than to me. So there is a Sanchayan Sen, who's a professor at IISc Bangalore. So if you have more questions, email him. Don't email me. So no, anyway, so just to say, you have one of the world's leading experts in these sorts of things, connecting networks with colloidal chemistry in like close to you. Okay, so this is like one area that the problems that I think about. The next sort of area that I think about is the things like network reconstruction. By the way, I should ask, so how much time do I have?
So you can go easily like for 1 hour, 1 hour 15 minutes.
Okay, sounds good. Yeah, thanks. So the next thing that I sort of area that I mentioned was network reconstruction in when you have partial information. So let me give you a concrete example. So this was the internet. When I say the internet, I mean like actual routers that transmit your information. When you send an email, the actual routers that transmit these information. And so this is the internet in the US somewhere in, let's say, 2004. And so these are the routers, and of course, different routers are controlled by different companies. So in the US, you have things like Verizon, AT&T, etc. In India, I'm sure you have things like I don't know, Reliance, maybe Vodafone, and so on, which control how information spreads through the internet. And but then the question you should ask yourself is, how did someone actually come up with this picture? Because companies are not going to tell you that these are the routers, these are my routers, and these are how they're connected, and these are how my routers, my company's routers are connected to these companies' routers. So the question is, how do you actually get a picture like this? And at a maybe more important level, why do you care about a picture like this? Why do people in, say, public policy care about these pictures? Well, I mean, they want to understand how robust is the internet. So, for example, if there is a hacker who's attacking a particular router in a company, can they take down the whole internet? So are there routers which are so central that if they're attacked by hackers or something, it could completely crumble the whole infrastructure? So these are the sort of questions that people in public policy, etc., are interested in. So they do want to get these pictures and understand the structure of the network. But on the flip side, companies don't necessarily want to release this sort of information. So this general area of trying to understand structure of a network when you only can maybe have partial information from it, this is called network tomography. And so this is another area that I've thought about with my friends, this Ram Rajagopal and Sebastian Rock, who are friends of mine when I was a PhD student and still are friends. Um, so this tomography, it comes from, this phrase tomography comes from medicine. So in medicine, so suppose you have a patient who goes to a doctor and they say, my liver is hurting. Can you help me figure out what is the problem with it? So there are two ways a doctor can approach this issue. There is the internal approach, which is like basically do surgery on the patient and see what is the problem with the liver. And then there is the external approach, which is put the patient underneath some sort of scanner. And so what the scanner does is it tries to illuminate the particular organ, like the liver, via lots of indirect measurements. So it takes, in math world, it takes two-dimensional projections of the liver using X-rays and so on. And then it tries to reconstruct a 3D image of these many 2D projections. So similarly, in the world of networks, there is the internal approach where each of these companies and their routers, they sort of tell the public policy person, okay, this is who I'm connected to, and this is how much information I typically carry, how many bits I'm carrying. Obviously, this is not feasible. So there is so then what is the version of this scanner in the world of networks? So this is something called end-to-end measurements. So let me just show you a picture. So what public policy people, what they're allowed to do is, so you have, this is a made up picture of of a network. So there is Shankar who's sitting on the green, who's sitting in his chair at that green point. And what he's trying to do is there are these bunch of red points, these other routers, and Shankar would like to get information about the connectivity between him and all of these red routers. So he wants to understand this actual structure. But he does not have access to the structure because these red things are controlled by companies. So what Shankar is allowed to do is he can send messages from himself to these red routers by pinging these red routers, and he can then see how long it takes. So it takes some time d1 to go to this router. It takes some time d2 to go to this other router, and so on. So he can measure the amount of time it takes for Shankar's message to go from himself to these other routers. So what Shankar observes is just the amount of time it takes for his messages to go from himself to these other routers. And using just this information, Shankar wants to magically somehow find this actual structure connecting himself to these other red routers. So this is what Shankar is interested in, and so these are the kinds of questions that I have thought about with my friends, and so can we recover this topology of these sorts of networks and so on? And sort of without going into detail, the answer is yes. You can propose algorithms that you can show work with high accuracy, and you don't require too many samples. But maybe the most interesting part of this research is many of these. I think there's some more chat message, but just give me one sec. Maybe the most interesting part of this research is it forced me to learn other areas of mathematics or maybe even biology. So the same sort of questions show up in the world of genetics, for example, or phylogenetics and evolution. So if you have a bunch of organisms, in this case, like apes, like gibbons, orangutans, gorillas, humans, and so on. So you have these species which exist right now. You can measure their DNA, and from the DNA, the question is, can you reconstruct how the evolutionary connections between these currently existing species? Which is sort of, at a high level, quite analogous to the questions that we were thinking about in the world of, like, let's call this broadly computer science. So you have information on these routers, and from this, can you actually find the underlying topology joining them? Okay, so is there some question on the chat or
So
anything?
the question is that how can you send a message to different routers? Won't they go to the same router?
No, good question. No, so there are ways to specify which router you're sending a message to. So you fix the bunch of routers that you're interested in, and then you specify, okay, I want to send it to this router. So these are the bunch of routers I would like to send it to, and then you send the message. And the way that this message goes is, I kind of skipped through this, but there is something called multicast routing, where when the message goes, it starts with one message at Shankar, and wish I had a 1 second. So just use this thing here. So every time, so you have a message starting over here. Every time it comes to a branch point, a copy is made, and one copy is sent down this branch, another copy sent down this branch. And then over here, again, one copy sent down this branch. So two copies are made in this case, another is sent down this branch, and so on. But the main thing is, once, if you look at the routers which are close in the network, then for a long time the same message goes, and then it only sort of two different copies are made right at the very end. So in some sense, there is correlation between the times it takes for messages to get to the routers. And so what we did was we used these correlations to try to get good algorithms. Okay.
So there is
Oh,
another follow-up question. So
okay.
how do we differentiate between the case where routers are linked via branches versus
Mm-hmm.
whether Shankar is sitting at a star topology with different
Mm-hmm.
routers being at different distance?
Uh, Different routers. Okay, wait, sorry. Could you say? Maybe I
Yeah,
should read
so
this.
how do we differentiate between the case where routers are
Mm-hmm.
linked via branches
Mm-hmm.
versus whether Shankar is sitting at a star topology with the
Mm-hmm.
different routers being at different distances?
Okay, good. So when I say you can propose algorithms to reconstruct the topology from Shankar to the routers, obviously you cannot do this perfectly in every case. So in some cases, things like the star topology, I mean, I think even there, given enough samples, you can say that, okay, just Shankar, and then you have all of these different routers that only come to Shankar and they don't actually connect to each other. So there is a way to differentiate this given enough samples. But yeah, one does need some assumptions on the actual structure of how the information is being passed and the structure of the topology to guarantee. So I can propose an algorithm, but again, great question. But if I want to say my algorithm is guaranteed to give you the correct topology of the tree, correct topology of the tree in this case, then I need some property. So for example, another issue is, so suppose you have just one point right in the middle over here, and that point there is no branch point, so you have a router right in the middle of this branch, and just the information then enters that and then continues. Obviously you will never be able to see the existence of this router, because the information just passes through it, and just based on the information at the endpoints, you won't be able to reconstruct such phenomenon. But yeah, very good question. Okay, so I think I have maybe two more, or maybe one more example. So another area that I have thought about is things like Twitter and flow of information. So there used to be a time in the 2009, 2010 when Twitter used to be something fun and didn't have such a big effect on our world in some sense. Now it feels like it has a massive influence on how we react, how politically polarized we become, and so on. But in the a long time ago, say in 2009, Twitter was mainly used for things like marketing, and it's kind of amazing how much money was being given to people to market. So, for example, this was in 2009. You have celebrities who, like Kim, in this case, Kim Kardashian, who just for 140 words on Twitter, they would get paid $10,000. So people were very interested in how information flows through Twitter, and in particular, trying to figure out who are the influential people on Twitter. So these are the sorts of questions people were interested in, and so these are the sorts of things that I work with people in the world of business school, for example, and probability. So Michael Steele is a professor at the Wharton Business School, and Tawhid Zaman, actually he moved from MIT. He's now in the Yale Business School. So they were interested in trying to understand and come up, maybe the most, to summarize, they were trying to come up with a better model of how information flows through Twitter. And so what do I mean by information flowing? So they were interested in retweet graphs. So given any topic and a particular time frame, like 4 or 5 hours, at that point, you could get information about all retweets about that particular topic in that time frame. And so once you get that, you can form networks. And when they did this, so Tawhid, he was working, I think, as an intern at Microsoft when he was getting this data. So what he found was that many of these networks had similar sorts of properties. So in particular, many of them had what one would call a superstar, namely 1 or 2 vertices with lots of people retweeting what they said. So he constructed lots of different retweet graphs. So he was something about Roger Federer, something about England. I think this was during the World Cup. Something about this BET Awards, and again something about the World Cup. So various different topics, things related to sports, entertainment events, and so on. So he just explored this data in a time range between 4 to 6 hours. And so I'm not going to spend too much time telling you about the findings, but what he found was that in many of these, so for example, for the BET Awards, many of these networks seem to show the superstar phenomenon. You have a few vertices. So here there is Lady Gaga, who was retweeting something about this BET Awards. She was then retweeted by Justin Bieber and Selena Gomez and so on. And then you have the rest of the people in this network who have reasonable degrees. So there are some people who are super popular, and then there are other people who are reasonably popular. And many of the models in the literature, they did not capture this sort of phenomenon. And so what Tawhid and J. Michael Steele, what they were interested in was trying to figure out models that could perhaps model such phenomenon in Twitter. So what did we do? So this is Professor Steele and this Tawhid. So what we did was we first developed a model that seemed to show a closer fit to the evolution of such networks. And so since I don't exactly work in the business school, for me, sort of the main motivation was to develop like mathematical tools. So in the world of probability. And so these tools turned out to be related to a completely different area, things like population models, um, like how, say, viruses propagate, for example. And so these sorts of models also turned out these sorts of models and the mathematical techniques related to analyze them turned out to be useful, for example, in understanding these Twitter models, and they turned out to be useful in a whole bunch of other settings preceding this. So the model itself was super simple. So let's say that, so we're trying to model how one can observe these sorts of retweet networks. So what we're going to do is we're going to make up a math model and see how well this does in trying to fit the data. So the simplest such model is the following. So suppose you have a superstar who makes up some topic, Virat Kohli says something, and then you have people who are going to retweet the same topic. So how are they going to retweet it? So each new person who enters the system to retweet, with some fixed probability, they retweet what the superstar, like say Virat Kohli, says. And so with probability P, they retweet what the superstar says. And with probability 1 minus P, they retweet someone else. Now, when people are retweeting a particular topic, it is maybe not realistic to say they randomly pick someone who's talking about this topic on Twitter and retweet what they say. They still have some feeling that they're going to look at the popularity of people and then retweet what they're saying, even if they don't retweet the superstar directly. So with this 1 minus P probability, they retweet some other person and they choose these other persons with probability proportional to their degree. So namely the number of other people who've already retweeted this person. And that's it. So this is a model of how a network evolves. And so there's only one model parameter, this P, which is called the superstar parameter. And so it's a super simple model of a network. And you could say, okay, so this is a simple model. Now, what can we do with this? So what we did, this is none of this is important, but this is just to give you a flavor of what do I mean by research, like the kinds of research I do. So first is we try to understand mathematical properties of such a model. So for example, what this theorem is, this is a theorem that means we prove this result. And what it's saying is I can tell you as this network becomes larger and larger, this network model becomes larger and larger, I can tell you various properties about this network model. So for example, I can tell you if you're interested in the number of people in this network model with 10 friends, I can tell you in the limit what this looks like. So we can tell you properties about this sort of network model. But then we can go back and see how well this network model does in trying to fit the actual data that people see. Okay, so for a whole bunch of events, we have the actual data. We have what the theoretical prediction would be based off a network model. And the basic punchline is this particular model, in at least the things that we saw, seems to give a much better fit to the data as compared to some of the other standard models in the literature. So I'm just going to show you some graphs. None of this is very important, but the main thing is in these pictures is the green dots represent the actual data. The red curve represents one of the standard models that is used in fitting such sorts of phenomenon. And the black curve in each of these graphs is what our super simple model predicts. Okay, so it isn't like this super simple model does great in many cases, but it does a better job than some of the existing models. So this is sort of the pipeline. So someone comes, say from the business school, comes to me with a particular model. Then I try to help them. So together we work on trying to understand properties of the model. And then we go back and see, does the model actually do anything useful? Does it do anything useful in the actual applications? Okay, so the final, I have maybe 15 minutes. So the final area that maybe I just want to tell you a little bit about, because everyone is thinking about this, is like epidemic models on networks. So this is a simulation from the statnet.org/NME, where the red people represent someone who has an infection, and when people interact with each other, talk to each other, then they could potentially infect other people. And so this is showing you how infections can spread through a network, through interactions between people. So eventually, starting with one red infected people, potentially the entire or a big part of the population can get infected. And so all of us know, unfortunately, over this last year, we know that when a disease progresses through a previously unexposed population, our world can be brought to a standstill. And so intuitively, how susceptible, like how possible is Shankar to get a disease? So obviously it depends on Shankar's own immune system, but to some extent it also depends on Shankar's sociability, like how much Shankar interacts with other people, how big a social group he has, and how often he interacts with it. And so the bottom line is the network structure in a population is also a key determinant in how quickly an infection could spread through a population. And so some of the things that I've done with people like Alan Sly, another friend of mine from grad school, and his students and postdocs, Danny Nam and Owen Nguyen. So what we tried to study were models of how infections spread on networks. So you have some sort of network that connects these people, and then somebody gets infected in the network, and then this slowly potentially spreads through the population. People get better, so it is possible that very quickly the infection dies out before it can really spread through the network. It stops. So you start with a few individuals in the population infected. Infected individuals could infect their uninfected friends at some rate, and infected individuals get better at some rate. And so the main sort of question we try to study is what are properties of the network that can tell you, so what properties of the network tell you whether this infection will quickly spread through the entire network or through a large fraction of the network, or whether it will quickly die out. Okay, and so we proved again math results about these sorts of things. And just to clarify, these are all mathematical studies, and one has to be careful. I cannot sit here and tell you, what we proved has direct relevance to, say, COVID, for example. So our main goal was to provide insight into these models of epidemics, and in some sense abstract away many of the complexities of the actual phenomenon and make a simpler math model which could potentially give insight that might help, say, people, and to sort of develop mathematical machinery that can hopefully be used to analyze more complicated models. So it provides insight, but in no way can one immediately claim that this is going to help public policy immediately. Okay, so I think so in terms of like research itself, the world of networks is super fascinating for me. There are so many different areas where mathematicians can contribute. So areas that I think, looking down into the next few years, things that I am very interested in are things like, for example, in our world right now, one could say that there are two epidemics propagating through the world. One is through the world of social media, like Twitter and Facebook, WhatsApp, and so on. And another is the actual infection, COVID, spreading through the population. So you have these two levels of diffusions going through a population, and they interact with each other. People say stuff on Twitter. This affects how people, their own actions, whether they socially distance themselves or say, oh, everything's okay, we should start interacting with people, or whether they decide to take a vaccine or not. So things on the social sphere influence people on the normal sphere and vice versa. So this is some area that I'm super interested in thinking about in the next few years. Similarly, I'm very interested in thinking about data coming from areas like neuroscience, where one is interested in brain networks. In particular, can you predict diseases like Alzheimer's, for example? Can one cure these diseases via targeted therapies at locations in the brain and so on, not specific to patients? So these are areas that and of course, many people have been hearing about deep learning, machine learning, neural networks, and so on. So, why do these work? Do these work? And if so, why do they work? So these are questions that I am interested in exploring. So maybe I have 10 minutes. So maybe in the last 10 minutes, let me just switch over now to some career advice. So I will say various things. So whenever I say these are things so all of these things are phrased. So these are more advice for Shankar himself. So these are things that Shankar made mistakes. And now these are whenever Shankar is feeling like he's stuck in life, these are things that Shankar tells himself. So these are general things, so most people realize these things only when they've gone through these things themselves. So just general things regarding career in some sense. And I don't necessarily mean just career for say math research or something, just generally career in any creatively challenging, intellectually challenging field. So, sort of the first mistake that Shankar has regularly made through life, one would say, is sort of focusing on the results versus the process. And so you kind of see um, these statements or quotations. So whether you see the Bhagavad Gita, so for example, your authority extends only to the performance of the action. Obtaining or not obtaining the fruit is never within your control. So over focusing on the results and not focusing enough on the process is a big mistake that Shankar has regularly made, starting from, let's say, even when Shankar was a student, like a high school student, and even now Shankar regularly makes. I mean, and you see this regularly even when you see things like what Virat Kohli or Ajinkya Rahane says so they say the same thing. So we obviously have the desire to win big tournaments, we want to give our best effort possible, but if you focus on things which are only based on success and number of results, you don't enjoy the process. And so Shankar has regularly, unfortunately, focused on results, and he's trying to change his behavior. And this sort of mindset, I'm not claiming that if you do this, it guarantees success. Obviously not. But what I will go so far as to say is this mindset is sort of the key to success in any creative pursuit, in the sense, if you don't have this mindset, then you won't succeed. If you have this mindset, then it is the biggest way to succeed. No guarantee of success, obviously. The world is uncertain. And so sort of maybe related to mathematics, things that I've realized when I was learning mathematics, and I'm trying to change this now. So there is this huge overemphasis on getting the correct answer. So we have a homework problem in, say, a class or an exam. We want to do the homework problem, get it, do the correct thing, and then move on to the next problem. Quite often Shankar rarely stops and thinks, this problem was amazing. It made me think about all these really cool things. So just do one thing, then do the next thing, and so on. And so quite often one loses the point of why you're doing, say, mathematics, which is exploring ideas, playing with ideas, imagination, and so on. And in many cases, we forget that there are many ways to do the same problem or understand the same set of ideas. And there is rarely one correct way to understand it. So one suggestion in this case is when you're taking a course or something, always remember that your professor who's teaching you, they have learned these concepts and they've mastered them in their way. And they're showing you one path to how to master these ideas, but then you have to figure out your own way to master these same ideas. So you have to work these things out yourself. Your professors are giving you a guide, a path, but at the end, it's up to you to figure out your own way of thinking about these things, and there isn't one right way. And so punchline is this process of exploring is much more important than this final answer. Okay, so that's the first thing. The second, I think I have only three main advice here. So the second thing is one of the most potentially annoying questions either Shankar asks himself or Shankar gets is, what is the use of this? So, I'm learning topic X, I'm learning topic Y, I'm learning, this subject. What is the use of this? Will I ever use this anywhere else? So this is again, I think, the wrong way of thinking about things. And so one reason I really like my own research, which is networks, is to a large extent it is a metaphor for learning and education. So in the world of networks, I think I've mentioned you can put in various very simple rules, but what emerges cannot be predicted. It's a much more complex phenomenon. Very simple rules give rise to very complex phenomenon. This is the same thing about education. So you learn some things, you learn, let's say a language, Hindi, Tamil, Bengali or something. Then you learn mathematics, then you learn machine learning and so on. So you learn all of these individual things, but what emerges in your brain and the kinds of ideas that you are able to come up with, that cannot be there is no simple relationship between what goes in and what comes out. And everything is connected and useful. So for example, I've given you examples of how there is a big connection between colloidal chemistry and network models. Similarly, in the world of probability, people have shown that there's a very deep connection between things like statistical physics and efficient algorithms in the areas of machine learning. Suppose a long time ago, Shankar was taking all of his courses like Hindi, Bengali, etc. And he was asking himself, oh, why am I doing my second language, third language? Why am I doing these courses? Well, I mean, all of these languages, understanding the structure of languages, they're super important in how many of the big tech companies make their money, like topic models in areas like Google, Facebook, and Twitter. And in my own research, many of the tools that I use, which I'm using them for areas like, let's say, business or sociology or political science, something called branching processes, their origins came in a completely different area. They came in the world of biology and genetics, and in particular, understanding how to model the evolution of populations. So the basic punchline is when you're in your own education, you need to develop your own mind map for everything that you learn. So there is this one example of a mind map in physics. This is this relativity, quantum physics, classical physics, and so on. So you need to develop how different aspects of what you're learning connect to each other. Okay, and then finally, and I'm going to conclude here. So finally, the mistake Shankar has always made is what one might call over planning or over optimization. So to a large extent, we have one might have like a 5-year goal. In 5 years, I'm going to do this. I'll have this internship, do this PhD, do this, have this job, etc., etc. But we have far less control on our own destiny than we imagine. And so there is, in a big scheme of things, there is no point in over planning your life. And humans have what's called bounded rationality. We can only take in so much information and deal with some limited number of factors at any stage. So in general, what I have found much more useful is sort of focusing on local optima, like trying to think at this stage in life, what is good in this stage in life, what am I interested in, what seem interesting. And somehow, if I can worry about local optima, think about the current state. Obviously, one should have some goals long term, but one shouldn't obsess about the long term goals. One should just focus on what's happening currently and then sort of have faith that it will work out in the end. Again, this doesn't guarantee that you will be successful, but as the Zen saying says, if you always have one eye on the future, you have only one eye to focus on the path. So sort of if both of your eyes are focused on the present, then you will hopefully have a much higher chance of success. Okay, so that's it. Oh no, I have one more. Oh right, okay. So last, maybe just one final thing about research in mathematics. So when I initially started thinking about my PhD and research, I assumed if you take mathematics courses, you feel like there are so many different topics, so many different problems. I thought that finding new problems to do research in would be difficult, but it's my experience has been now it's the opposite. Our ignorance in so many areas is so much that often it's the opposite, in the sense there are so many interesting problems. What we need to work on is what is actually exhausting. It's not whether we can find something to work on, but what should we work on. So decision fatigue is what's exhausting. Okay, sorry, I went 20 seconds over time. So, okay, any questions?
Thank you, sir. It was a really wonderful talk. Like the way you started from tsunami in Japan and Egypt movement, starting from like Twitter retweets and went to Kim Kardashian advertisement campaign. Like it was really wonderful. Like looking at so many examples, the graphs and the animations of networking. Like we totally understood it. Okay, how does this network influence our day-to-day life? It was
Okay,
really
thank you.
wonderful, and I think like everyone is like now interested and motivated to read more about networks. So,
Okay, thanks.
if you have
Thanks.
any
Yeah,
questions, then you can ask Professor now, or you can put it in the chat box also. So we are open for a short question and answer session.
super. My talk is so clear that crystal clear.
Like the way you included diagrams and animations, I don't think people have to like they won't have any doubts anymore.
It's like picture speaks 1,000 words. So from that
Exactly, that's
framework,
true.
my talk is like Mahabharat with only 1 hour.
So if you have any other questions further on when you read about it, you can put send to us an email and we will get it answered by Professor.
Mhm.
So
Yeah,
I think we can come to the close of this talk. So like join me with like for thanking the professor. So it was really wonderful to have you in STEMs. So
okay,
we
thank you.
will have our next talk at 6:30 by Professor Apurva Khare of ISC Bangalore, who will talk about an interesting problem named as polymath problem project, which you will see like how he described and how the team of led by Professor Terence Tao solved that problem. It was really wonderful having you. Thank you,
Okay, thank you.
Professor.
Yeah,
Thank you
yeah,
very much,
thanks.
Professor.
Yeah,
It was
sure.
lovely.
Yeah, nice talking to you all. Yeah, thank you.